Dan Shiebler. I hope I'm pronouncing that correctly.
That's right.
Who's talking about categorical stochastic processes and likelihood. Go ahead, Dan.
All right. Is everybody able to hear me? Great. And you can see my screen? Excellent. All right. Hello, everybody. My name is Dan. I'm a PhD student at Oxford, and I'm going to be talking about a stream of work that kind of came out of an observation that there's a pretty prolific stream within the realm of categorical machine learning that focuses on understanding the structure of optimization update steps in the realm of automatic differentiation or backpropagation. And there's also a stream that explores categorical probability and statistics, Bayesian statistics, different kinds of model updates in response to data. But there's this sort of connection between this optimization perspective and this probabilistic perspective is reasonably unexplored. So this work was my attempt at bridging these two, and to some extent. So to just kind of set the stage, two categories that are reasonably important, especially in the optimization realm, are uke and what I'm calling para-uke. So these are basically categories of differentiable functions between Euclidean spaces. For simplicity, we're just limiting to r to the n for some n. Para-uke is, I believe, introduced in the backprop as functor paper, and sort of called a few different things in a few different papers. But basically, each morphism in para-uke is indexed by another Euclidean space. So it's these parameterized differentiable functions as opposed to just normal differentiable functions. And when you compose two parameterized differentiable functions, their parameters compose as well, and you get like a larger function with more parameters, similarly to just how a neural network or something like that would compose. So the backprop as functor paper describes a functor from this category para-uke to a category learn, where morphisms are these tuples of maps, which are the parameterized function, and then a couple of other functions to represent the update steps that compose in the way that backpropagation composes. And this is a very lens-like structure. That there's some follow-up work that shows the relationship between this structure and lenses, and then some other kind of optic connections. And the core insight is that the forward pass and the backward pass of neural networks have this kind of core functorial relationship. Now, one thing about this work, and then also there's a couple of other works that are focused more on automatic differentiation in the abstract as opposed to just backpropagation and neural networks in particular, is that there's the notion of these things being optimization as opposed to just machine learning in general. And the bridge between optimization and machine learning, or optimization and database techniques, is that of an error function. That there's some sort of error function that describes the difference between what your model is producing, what you want it to produce, and the gradient update steps and the structure of how you want your model to evolve over the course of the optimization are dictated by the structure of this error function. And in these works, this error function is usually assumed to be given. The goal of this work is to try to change what our domain of the backpropagation functor is, so that it is a category where our error function comes naturally. And in order to do that, we're going to turn to maximum likelihood, which is one of the ways that error functions come about in practice. That is, we have some statistical model we set up whichever set of equations will be necessary to maximize the likelihood of some observed data with respect to the parameterized distribution that model describes. And this procedure allows us to define an error function that is the difference between what our model produces and what the data is that we observe. So to describe the maximum likelihood and the relationship of maximum likelihood back to learning models, we turn to categorical probability. So one thing that I'm going to be using a lot is this category UCMES, which is basically the same as the category of measurable functions, except we're limiting our objects to just Euclidean spaces with their Borel sigma algebras, and we're requiring that morphisms are differentiable as well as measurable. So this will allow us to have a sort of nice bridge between these categories that rely on differentiation, categories that rely on measurability and probability. And so we have Stoke as well as an important category in categorical probability. It's the Kleisli category of the Geary monad. There's a lot of interesting subcategories of it that we need for all kinds of different things. The morphisms in Stoke are Markov kernels, which are essentially parameterized probability measures. And they compose with this integral structure that we see. So basically what the core of this construction is based around switching the script a little bit on Stoke. In Stoke, we're talking about parameterized probability measures, and we want to get to some place where we're talking about parameterized functions, and the sort of intermediate space between these is parameterized random variables. And a parameterized random variable, or a family of parameterized random variables that satisfies some nice set of properties, is the stochastic process. So what we're basically doing here is we're going to work with this category of stochastic processes, which we're going to be building out by parameterizing the arrows in UCMES with a probability space. So the composition in our para omega UCMES category is very similar to how composition works in para. We are building up our omega, our sort of probability space, as arrows compose. So each arrow is sort of this jointly Borel measurable function that is for any fixed XA in RA, we get a random variable that's going to be over a probability space based around this omega to the n, which I'll guess it probably makes the most sense to describe this way. We can show that there's a relationship between this para omega UCMES category and our category Stoke of Markov kernels through this product measure relationship. So given a probability space, some topological space omega, and our Borel-Stochastic algebra, and a probability measure mu, we can form a product measure by applying this kind of simple equation in order to build a probability space based on omega to the n. And this allows us to continue expanding the set of probability spaces that we're mapping over, and have the stochastic processes compose as if each of the random variables that is indexed by any morphism is independent, which then allows us to define this functor from para omega UCMES into Stoke that sends a stochastic process to its corresponding Markov kernel. So para omega UCMES is stochastic processes. What we want in order to fully expand to a space where we're going to be able to map into differentiation and reason about machine learning models is going to be parameterized stochastic processes, or parameterized random variables. We can do this by applying the para construction once more. And we now have these arrows in our para UCMES being these parameterized stochastic processes. I think the simplest way to describe these is through an example. In univariate linear regression, which is just the sort of the simplest kind of statistical model that we can describe, we have sort of three arguments when you view it through this random variable stochastic process lens. We have our parameters, we have our inputs, and we have our source of randomness. Then our actual stochastic process itself has this kind of structure where we have this expectation term, and then we have our noise term, which is how the randomness itself is captured. For any set of parameters, our univariate linear regression is a stochastic process. For any pair of parameters and inputs, our univariate linear regression is a normally distributed random variable. And this univariate linear regression is then an endomorphism on R. So the arrows in our para omega para UCMES are explicit representations of a parameterized model along with the distribution that describes its outputs. So this now allows us to loop back to where we were at the beginning. If our goal is to replace the domain of this backpropagation functor with the category such that our error function falls out naturally, our refined goal is now to find some subcategories of our para UCMES that can take para UC's place as the domain for the backpropagation functor, that have a structure such that we can define likelihood functions over them, and then have the error function fall out of these likelihoods. So there's two ingredients that we need to do this, to define this mapping from our para UCMES to our category of learners. The first thing that we'll need to do is to define an inference function. That basically we need to take this gnarly stochastic process thing to actual parameterized functions. And so we'll be using expectation to do that, so I'll describe that in a second. The other thing that we're going to need to be able to do is to pull our error function out of our likelihood functions that are associated with the push forward measures of each of these stochastic processes. And in order to pull out an error function in a way that is well behaved and allows us to define this backpropagation or kind of functor, we'll need each of the arrows in the category to have likelihood functions that are of a similar form and share the same error function. And I'll describe exactly what that means in a second. So first, the expectation composition condition, which is required to allow us to extract our parameterized function from our stochastic process, is relatively simple. Basically, we're just saying that if we take the expectation along our randomness and map our stochastic process to parameterized random variables by just taking the expectation of each of the random variables that are parameterized, map it to a set of parameterized functions, then this mapping is functorial. And this there's a lot of classes of random variables that satisfy this, including anything that has linearity. The likelihood condition and error function condition is a little bit more subtle. Basically, we want to extract an error function from our likelihood functions that has this kind of structure where our error decreases means likelihood increases. So just a quick note, this expression on the left is the radon Nikodym derivative with respect to the Lebesgue measure. That is generally how likelihood functions are described. Likelihood is really just a synonym for that. So we take that derivative of our push forward measure and that forms our likelihood function. And we want our likelihood function to be in a structure where we can express it. We can pull out an error function defined over the expectation of a random variable. And this seems a little esoteric, but there's a lot of likelihood functions that do satisfy this. For example, anything that's normally distributed will allow us to pull out mean square error as a natural error function. There's things with Bernoulli allow us to pull out cross entropy. There's a whole family of these sorts of distributions that imply a natural error function. So in order to categorify this and to have a kind of relationship whereupon the each of the different arrows in our category are going to have this sort of structure, we're introduced this notion of our para-para-Eukmez R structure, which basically is just the set of arrows in para-para-Eukmez that have likelihood functions at all. And this is not given. Most, I guess, many arrows do not. Most critically, any of the identity arrows in para-para-Eukmez do not have associated likelihood functions because their push forwards are Dirac measures. And so for this reason, our para-para-Eukmez R is actually a monoidal sub-semi-category rather than a subcategory. But that's not tremendously important because we can we could do the structure that we need within semi-cat rather than cat in order to pick out the set of arrows that we're interested in. So this is a lot of text, and it's not tremendously important to get the general gist of it. But essentially what we can say is that this property where likelihood functions have this associated error function is preserved under composition in tensor. So we can find these categories based on a set of generating arrows that have this expectation composition condition and have this error condition, and then allow us to describe these as what we were calling marginal likelihood factorization categories. And then for any such marginal likelihood factorization category, we can now define basically what we started with, which is this mapping that first applies expectation to get us back to para, and then applies a backpropagation functor under this marginal error function associated with our marginal likelihood factorization category. So when we do this, we've sort of effectively removed the error function from its original status as a user-provided parameter and replaced it with an inherent property of a marginal likelihood factorization category. I guess I have 2 minutes, so I'll give the example that I had. So one example is this category para-para-Eukmez N, which is our category. I love the names are terrible, I know. Which is a category of Gaussian preserving transformations. Basically, we have maps that preserve Gaussianity, where if you have a Gaussian random variable and you apply this map, you get a Gaussian random variable out of it. Then we can build a monoidal category of these kinds of transformations, of these kinds of stochastic processes. And when we do this, we get a marginal likelihood factorization category where the error function is mean squared error. Cool. All right. I guess I'll take questions. Thank you.
Thank you. Let me see if I can do the reaction quick. Yes. Thanks very much. So if there are any questions, please unmute yourself and ask. So Dan, while we're waiting for somebody to pipe up, let me ask a quick question. So you've restricted yourself to Rn as the objects, right? Which is presumably so that you can define differentiation. Would it be
Yes, that's right.
to generalize it to say manifolds?
Yeah, that I don't foresee any problems necessarily with doing that. I think that there's a couple of times where um, the fact that Rn is very simple makes some of the proofs a lot easier, especially with the tensor product and the fact that the Borel sigma algebras have nice behaviors under tensor. I don't think I don't think there's any I don't foresee any fundamental issues with doing it. Just the technical details of the proofs would probably be a bit more challenging.
Imagine that you'd be fighting with geometric measure theory and Jacobians of matrices and and coordinate charts. But conceptually, yes, I would think it should all work nicely. And by sticking to RNs, do you lose some things like co-products or?
Yeah, that's a good question. Yes, I think there's there's some Cartesian structure that ideally I'd like to be able to work I'd like to be able to work with a compact closed category instead, and work with like quasi Borel spaces and something like that. I think that's the main pain that I feel. I'm not sure if when I sort of think about the direct extension of this, I guess that doesn't exactly answer your question. I don't feel the pain of the sticking with the Rn, but I do feel the pain of sticking with Borel spaces rather than quasi Borel spaces.
Okay.
Quick question. Does this have any? Does it have any obvious or non-obvious applications to machine learning?
Yeah, that's a great question. So I tried some experiments with this. The main application here is that this is demonstrating a notion of how likelihoods compose, like in sort of a direct machine learning setup. There's neural networks compose once you sort of treat them just as their expectations, and then only treat the very last output as something that's probabilistic. Whereas here we have this notion of if you have one neural network where you've modeled it as a probabilistic model, another one you've modeled as a probabilistic model, how does then the output distribution actually change? So I ran some experiments that using like TensorFlow probability to look at how this worked. I'm not entirely sure what the applications of this would be. There's like a composition of uncertainty in there somewhere, but I have yet to come up with like experiments on real data where I would expect this would do something that I couldn't do otherwise.
Cool. Thanks.
Compositionality is bound to be useful one day.
Yeah. I think so too.
At least, I guess I'm preaching to the choir here.
Besides, just because it doesn't tell you something you couldn't do otherwise doesn't mean it doesn't organize something you could have done otherwise in a nicer way.
Totally.
Yeah. It seems like something that helps you choose the right loss function, which right now is an ad hoc.
Interesting.
You pick the one that works best on the data you have. But here it's like, pick a statistical model of the data generating process and back out what was the right loss function.
Great.
Who said that? That was a very insightful.
That was James.
Oh yeah, I didn't have my
Yeah,
video.
I just saw a question in the chat about the experiments. They're linked in the paper. Just mentioned that.
So very nice talk, Dan. I liked everything
Thank
except long names, which look like they were designed to be sung by Freddie Mercury. But, but I guess that's what happens when you compose names.
Yep.
Okay, if there's we have a minute for questions.
14 hours.
No? All right, then let's thank Dan again. And I actually have my sound on so I can clap. Thanks very much. Oh, very interesting.
Thanks.